myself from some normal requirements of a data-rich talk. This was very much an idea talk. And I'm really kind of throwing a potentially crazy idea out there, potentially good idea. I hope it's a good idea. It's something I've spent a lot of time thinking about. So this is very much just kind of pitching something to you guys. And that idea, is that polar auxin transport, or protein-driven auxin transport, could be responsible for vessel patterns. So I think that vessel patterning has inspired many of us in this field. I know that it has inspired me. So there's a tremendous amount of natural variation out there in vessel patterning. And by vessel patterning, I really mean the size of vessels and their spatial distribution in wood. A quick shout out to this Inside Wood database, if you are not familiar with it, and many thanks to Elizabeth Wheeler and everyone who curates this. It's a fabulous online resource for anyone interested in this stuff. Just another kind of eye candy picture of vessel patterning. Can everyone hear me away from the microphone? Great. So in addition to this just being kind of aesthetically inspiring, well, we also know that there are major implications of vessel patterning for wood ecophysiology, for wood evolution, for utilization of wood as a material, but I would argue that its biological basis is essentially unknown, not even poorly understood, but basically unknown. So I'm going to propose that auxin transport might be a good candidate to look for in terms of where this is coming from. So just a little bit of basic background on auxin if you're not familiar with this area. There is a tremendous amount of auxin in the vascular cambium. A couple people have measured this. I am one of them. I, in particular, am measuring it in the earliest xylem derivatives of the vascular cambium. It's not entirely clear where the peak of auxin is relative to the actual cambial initials or the developing xylem. I would argue it's heavier in the developing xylem side. But one thing you might note here, so the understanding currently is that all this auxin is synthesized in rapidly expanding leaves and kind of channeled down into the vascular cambium. There are reasons to maybe question that. We can talk about that later if you're interested. But assuming that is true, it requires a little bit of a slowing in that downward transport for it to collect to these levels in the vascular cambium. And I've done some radioactive auxin transport assays that support that idea. So transport is moving down through the vascular cambium, through the developing xylem derivatives specifically, but it's moving really slowly. So first just imagine this downward cylindrical stream of auxin. So you may be thinking, well, duh, of course it's involved in vessel development. That is a perfectly reasonable approach to starting off thinking about this. We know that auxin is very much at the basis of vascular patterning, and there are a couple of beautiful examples of this worked out. This is a review paper that covered some of this really classical work. So even though this is a symposium honoring Bailey, I have to give a shout out to Steve Sachs, who pioneered this idea of the canalization hypothesis, just ingenious, brilliant insight into a process that we have now watched be elucidated down to a very fine molecular level. So here, this is showing a classical experiment many of you may be familiar with, where an exogenous source of auxin applied to a wounded stem leads to the differentiation of vascular bundles that differentiate toward that source of auxin. So an existing vascular bundle will see new vascular bundles differentiate from it toward that source of auxin. Note that it's not happening up here. I'm going to kick that can down the road until after this if you want to talk about it. So this is very well understood, and we've watched in the last 2 decades, a little bit less than that, the molecular underpinnings of this be just absolutely beautifully worked out. So we know that a family of proteins, the pin proteins, they're efflux proteins, they move auxin out of cells. They are able to be asymmetrically localized in the plasma membrane. They're actively put in and pulled out and relocalized, repositioned in the plasma membrane in response to all kinds of things. And this is really at the heart of just about any plant developmental system that involves an axial direction, axially oriented developmental processes, which in plants is many things. So here you can see that asymmetric localization. I just want to zoom in here for a second on what's going on at the shoot apical meristem. And and we will get to woody plants in a second, I promise. So these pin proteins are asymmetrically localized in the epidermis and the surface, these surface cell layers, really the surface cell layer, of the shoot apical meristem, such that a convergence point forms that reaches an auxin maximum. And from that point forward, auxin is canalized, channeled. You get bogged down in the terms, but I would prefer not to. It's channeled down into a narrow file of cells that then differentiate into the procambium, which then goes on to differentiate into a vascular bundle. This is the basis of how plants determine where veins form, essentially. It's been beautifully worked out in the shoot apex and in leaves in particular. There were a couple tools that made this work possible, and they inspired much of my future work on this. One of them was an auxin-responsive promoter called DR5. So it's a promoter that indicates where a genetic response to auxin is occurring. It's a visual cue for where that's happening. Another is the ability to subcellularly localize the pin proteins. So first there were antibodies generated against them. You could guess all of this work took place in Arabidopsis. Later there were pin protein fusions, GFP and even some YFP. Just an absolute amazing body of work came out of these tools. So I wanted to get that DR5 promoter and ideally be able to subcellularly localize pin proteins in Populus. Populus genome was sequenced right around when I finished my PhD, and I kind of did a huge shift to start looking at this. So with the help of a collaborator, colleague, Andrew Groover at UC Davis, we put the DR5 promoter into Populus. I've published some of this, and I want to spend a little bit of time on this slide to make sure everyone's oriented here. So these are Populus shoots. These are shoot tips of Populus, cross sections located just beneath the apex. These are vascular bundles, individual vascular bundles. Before the cambium has really formed in a continuous ring. So this is zoomed out a little bit. These are individual bundles. You can see what I'm calling the nascent cambium. The structure of the actual initials hasn't quite formed yet. The downward transport of auxin, the signal of that, actually precedes evidence of a structured cambium, and that is exactly as we'd expect. So there's a lot of cool stuff that we could talk about associated with that. These are bicipitally downward transporting strands of tissue-moving auxin. What I want to propose that is potentially a great idea, potentially a crazy idea, is that there is a subsequent canalization process of auxin here that involves vessel differentiation specifically. That the canalization of auxin down through a single file of cells is what allows for the axial alignment and the axially aligned differentiation of vessel elements that leads to vessels. That, if you want to think about it, is one of the hallmarks of the differences between a trachea-bearing plant and a vessel-bearing plant. Tracheids are perforate. Vessel elements are aligned on top of each other. They lose their end walls. They have to develop in perfect axial alignment for that to work. What better candidate to do something like this than auxin? Now, of course, this isn't the only reason, although some of this is just logical. It makes sense. But, of course, it's not the only reason that I think this. The other main reason that I think this is what Populus wood looks like if you apply an auxin transport inhibitor to it. So this is normal Populus wood up here. Down here you see wood under the influence of an auxin transport inhibitor, a chemical auxin transport inhibitor. It's called NPA, naphthalamic acid. It's fun to say. It takes about a month to get to the point where you can say it properly. So this is the auxin transport inhibitor applied in a ring. I was really just kind of playing around with this based on one paper that I'd seen. I'm not the first person to have done this. I seem to be the first person that has cared about it as far as I can tell. But I more recently applied it in a much more systematic fashion. There's a lot of stuff going on here that I'm not going to talk about. If you're curious about it, and in particular some of the hydraulic measurements that I made, you can check out this paper recently in AJB. I applied it in this case in longitudinal strips, so in a fairly long stripe along the outside of the stem, because I wanted to look at some of the hydraulic implications of this. But what I mostly want to show you here is that there are a couple different types of controls you need to do. There's a lanolin plus plus DMSO, which is the solvent that you need to use for NPA. There's a lanolin control where it's the exact same chemical matrix with everything minus the NPA. So that is shown here. And then there's the opposite side of the stem, which received absolutely nothing as another control. There are actually really interesting effects of the control treatment, which I will not discuss now, but the salient point here is that there's absolutely no effect on vessel structure. The only part of this treatment that affects vessel structure is the NPA. Now, what you can see here, I have lots of measurements, but you can see it with your eye. The vessels are smaller. They're much more highly clustered. Because of that clustering, they're angular in cross-section. I know nothing about their pits, although I would like to know something about their pits. If you zoom mentally in on this, if you just kind of squint and picture just this, you might think you're looking at tracheas. Some of the treatments were so extreme that I thought, God, I wonder if I just managed to create a little patch of tracheas in this tissue. Everything I've looked at so far has suggested they are perforate. So if you're familiar with this technique to measure vessel length, this is a silicone perfusion. It has a fluorescent additive to it. You force under pressure silicone into the cut end of a stem, and the silicone is only able to go as far as the vessel. When it reaches the end of a vessel, it is unable to move through the pits into the next vessel. So if you cut progressively further and further away from the point of injection, you can see vessels drop out, vessels are empty, and that indicates that you passed where an end wall was. So the gist of this is that the normal, typical vessels formed before the application of NPA have typical lengths. They range from 1.5 to up to 10 centimeters in length, which is typical for populous stems of this age and size. The aberrant vessels, as I call them, down here are all empty. They were all under 2 centimeters in length. They're several cells long, as far as I can tell. There are a couple of points to note about this. This is a crude technique. You're slathering a goopy chemical on the outside of a stem. There's no wounding involved, but there's diffusion in places you don't want it to go. So it's also, stems are remarkably robust against this treatment, which is important to keep in mind before you want to conclude that this is a really simple magic bullet explanation for this. But I wanted to take a much more refined approach to modifying auxin transport and try and study this more. So one first question is, which pin proteins make sense to look at? This is some work that was done in my lab quite a while ago now, but we characterized the expression levels of all the pin proteins. It looks like pin 1, coincidentally, was a reasonable candidate to focus on. And just real quickly to get to a conclusion here, we created these RNAi lines. We created RNA interference lines with reduced pin 1 expression. Kind of a shot in the dark. There are 16 pins in populace. We successfully reduced pin 1 expression by about 80%, so it was down to 20% reduction. Now you might argue, well, the other pins might jump in and take over or supplement and bring transport rates back to normal. But in fact, there is a physiological phenotype in these plants. They have markedly reduced auxin transport rates. So this is the 50% mark of the wild type rate of transport. This is with a radio-labeled auxin transport assay. The 3 RNAi lines that I've been working with have around 50% reduction in transport rates. But they look totally normal. There's absolutely no morphological or anatomical phenotype to these guys. What I would conclude from this is that it isn't the rate of transport per se, and I'm not even sure how much concentration per se is the issue. What's been perturbed in this system is the ability for those cells to canalize auxin. It's the ability of those cells to actually channel auxin down into a narrow file. So you want to picture, 30 seconds left. If we go back to this guy, maybe this one. Picture auxin being channeled down through vessels. And now picture that being slowed and that there's the lateral spread of that auxin. So it's all about the symmetrical or asymmetrical localization of the pins and how perturbing that affects the ability of auxin to be effectively channeled down through narrow files that we're preventing. But there's actually a lot going on with this. So in conclusion, like I said, this is an idea talk. I want to suggest that polar auxin transport is a really good candidate for regulating regulating the patterning of vessels in woody tissue, both because of its role in establishing axial continuity. I mean, that's what auxin does in plants effectively. But it also provides a really tantalizing link developmentally between developing foliage, which is where the auxin is coming from, and the stem that's developing beneath it. And those two things need to be developing in concert, especially when you're talking about hydraulic supply. Subcellular localization of the pins is where we need to go with this. I am not doing that. It's not in my wheelhouse. If anybody is a protein or in particular antibody generation expert out there and is interested in this, I'd love to talk to you. We're doing a couple things in the near term on this that I'm not going to take the time to mention, and I just want to have some acknowledgments. A postdoc from quite a while ago developed these RNAi lines, fabulous undergrad student in